there is a secret world hidden just beneath the surface of reality. It's a world where things don't behave as they should, where particles can be in two places at once, and where the very fabric of space and time seems to bend, twist, and fold. This is the strange realm of quantum mechanics, a place so bizarre and mind-bending that it has led scientists to question everything we think we know about the universe. But maybe, just maybe, it's the mysteries of this quantum world that can help us relax, let go of our worries, and drift into the peaceful embrace of sleep, the strange dance of particles. Superposition. Imagine for a moment that you are a tiny particle so small, in fact, that you can't even be seen with a microscope. In this quantum world, you don't follow the rules of classical physics. No, here, you're special. You are everywhere at once. In the realm of quantum mechanics, this phenomenon is known as superposition. A particle, such as an electron, can exist in multiple states at the same time. It can be both spinning clockwise and counterclockwise, both on the left side of the room and the right, all at once. It's only when we try to measure its position that it chooses where to be, collapsing into one state and leaving behind all its other possibilities. Now, imagine that you're not just any particle. You're the very air in the room, the breeze coming through the window, or the cup of tea on your nightstand. In this quantum world, you too would exist in a state of superposition. One moment you are beside your pillow, the next you are at the foot of the bed. And yet somehow you experience none of this chaos. It feels perfectly normal. Because in quantum mechanics, the act of measurement is everything. This paradox doesn't just apply to small particles. It stretches across the universe, bringing us to question what we really know about the reality we live in. The cat that is both alive and dead. If you're finding this all a bit overwhelming, let's ease into it. There's a thought experiment that can help us understand the perplexing nature of quantum mechanics. It's called Schrödinger's cat. In this experiment, a cat is placed inside a sealed box. Along with the cat, there is a radioactive atom, a Geiger counter, a vial of poison, and a hammer. If the Geiger counter detects radiation, it triggers the hammer to break the vial of poison, killing the cat. But here's the catch: quantum mechanics tells us that the radioactive atom can be in two states at once, decayed and not decayed. So until we open the box and check, the cat is simultaneously alive and dead, existing in a state of SUPE, RPOSIT, ION. Now, this doesn't mean that there's an actual cat inside the box in two states at once. What it means is that at the quantum level, particles exist in multiple possibilities, and it is only when we observe them that they choose one outcome. Until we check, the cat is both alive and dead. It's not just science fiction. This paradox lies at the heart of quantum theory, and it shows just how strange and unintuitive the universe can be. But just as the cat is both alive and dead, so too are we in a way. We live in a world where the past, present, and future are interconnected, and what we think is real might not be so certain at all. Imagine letting go of all your fixed ideas about what should be and accepting that the universe operates on possibilities, not certainties. Maybe, just maybe, that is the key to falling asleep, releasing control, and letting yourself float in the unknown. The particle wave duality now. Let's move to a different paradox, one that involves the wave-particle duality. This paradox reveals another surprising fact. Light, the very thing that allows us to see the world around us, isn't quite what it seems. When light is observed as a wave, it can behave like water waves, rippling and spreading out. But when we look closer, light behaves as though it's made of tiny particles called photons. How can this be? How can light be both a wave and a particle at the same time? This is a central mystery of quantum mechanics. The famous Double-Slit Experiment demonstrated this paradox. In the experiment, light is shined through two slits onto a screen, and instead of producing two bright spots, as we'd expect from particles, it creates an interference pattern, as if the light is behaving like waves. But here's the truly weird part. When the light is observed, it behaves like particles again, forming just two bright spots instead of the interference pattern dot. In other words, light acts differently depending on whether or not we're looking at it. It's as though the very act of observation changes the behavior of the universe. And this is where it gets deeply fascinating. The quantum world is not simply about what's happening out there. It's about our interaction with it. Our awareness, our attention shapes reality. It's almost as if the universe is asking us to slow down and realize that we are part of this grand, interconnected dance. We can stop trying to control every aspect of our reality. We can step back, take a deep breath, and accept the ebb and flow of life, the waves of light, the particles of thought, all swirling together in one beautiful, ungraspable moment. Entanglement. Instantaneous connection across space now. Let's move to another mind-bending idea: quantum entanglement. This one takes us even deeper into the heart of quantum mechanics, where particles can become entangled with one another, creating a connection that transcends space and time. Imagine two particles, let's call them A and B, created together in a way that they become linked no matter how far apart they travel. If something happens to particle A, particle B will instantly respond, even if it's light years away. It's as though the particles are communicating faster than the speed of light. This mysterious connection happens so instantaneously that it defies everything we understand about causality and the speed limit of the universe. Einstein famously called this spooky action at a distance, but it's a real phenomenon that has been experimentally verified. It's as if the universe itself has found a shortcut through space and time, allowing instantaneous communication across vast distances. But here's the catch. No matter how hard we try to measure or understand this connection, we can't use it for practical communication. The entanglement doesn't carry information in the conventional sense. It's as if the universe is whispering to itself, sharing secrets that we can't fully comprehend, just like how the particles in quantum entanglement are linked in ways that defy logic. We too are connected to each other and the world around us in ways we don't fully understand. Perhaps as you drift off to sleep tonight, the deep, cosmic connection between all things might remind you that you're not alone in this vast, mysterious universe. We are all part of something greater, something infinite, the uncertainty principle. The limits of knowing. Lastly, let's talk about the Heisenberg uncertainty principle. This is the idea that there are limits to how much we can know about a particle's position and momentum at the same time. The more precisely we measure one of these properties, the less precisely we can measure the other. It's not a limitation of our technology. It's a fundamental property of nature itself. This principle challenges the very foundation of how we think about the universe. In the classical world, we believe that if we know the position and speed of an object, we can predict where it will be in the future. But at the quantum level, that certainty disappears. The universe itself is fundamentally uncertain. Perhaps this uncertainty is a reminder that we, too, can't always predict the future. We spend so much time trying to control our lives, planning every moment, every decision. But just like quantum particles, life is full of uncertainty. And maybe that's okay. Letting go of the need to control everything could be the key to falling asleep. Just as quantum particles exist in a state of uncertainty until observed, we too can embrace the unknown, accepting that there are forces beyond our control. There's peace in that. The quantum world and the sleep of the universe. As you close your eyes tonight, think of the quantum world, where particles float in a haze of possibilities, where light can be both wave and particle, and where time and space can stretch and bend in ways that defy logic. Think of how the universe is filled with strange and beautiful mysteries that we may never fully understand. And as you drift off, remember that in the quantum world, everything is connected, everything is possible, and sometimes the more we don't know, the more we can rest. So let yourself be like a quantum particle, suspended in possibility, embracing the uncertainty and peace of the universe. The paradoxes of quantum mechanics are not puzzles to be solved, but wonders to be marveled at, just like the calm, infinite expanse of sleep waiting for you. Have you ever laid in bed at night, staring at the ceiling, wondering if the world you live in is actually real? Or if maybe, just maybe, you're living in one version of a million different possibilities? Tonight, we're going on a soft journey into the strangest parts of science, the paradoxes of quantum mechanics. So close your eyes, relax your mind, and drift into the mysterious universe where particles act like waves, and cats are both alive and dead until you look. The universe at the smallest scale. Let's begin with something very small, so small that you can't even see it under a regular microscope. Everything in the universe, including you and me, is made of atoms. And those atoms are made of even smaller things: protons, neutrons, and electrons. But here's where it gets weird. When scientists tried to understand how these tiny particles behave, the rules of regular physics stopped working. Instead of acting like solid balls, electrons sometimes act like waves spread out in space. Sometimes they're in more than one place at the same time. This kind of behavior is explained by something called quantum mechanics, a branch of physics that deals with the tiniest things in the universe. But instead of bringing clarity, quantum mechanics brings mystery. The mystery of the double-slit experiment. Let me tell you about one of the most famous experiments in physics. Imagine you have a wall with two small slits in it, and you're shooting tiny particles, like electrons, at the wall. You expect them to go through either one slit or the other. But that's not what happens. When no one is watching, the electrons behave like waves. They go through both slits at once, interfering with themselves and creating a striped pattern on a screen behind the wall. But when scientists place a detector to observe which slit the electron goes through, it behaves like a tiny solid ball. Again, and only goes through one slit. The interference pattern disappears. This simple change, just watching completely, changes the outcome. The experiment suggests that observation affects reality. But what does it mean to observe? Does the universe know we're watching? Schrödinger's cat, both alive and dead? Now let's take this weird idea and bring it to something more familiar. A cat. Imagine a cat locked in a box with a tiny radioactive atom and a vial of poison. If the atom decays, it triggers the poison and the cat dies. If it doesn't, the cat stays alive. But here's the twist. Quantum mechanics says that until we open the box and observe it, the atom is both decayed and not decayed. That means the cat is also both alive and dead at the same time. This strange thought experiment, called Schrödinger's cat, isn't meant to suggest real cats are zombies. It's meant to show how absurd quantum behavior becomes when applied to everyday objects. Still, it leaves us wondering, is reality only real when we check on it? The role of the observer. Let's pause for a moment. Imagine you're lying under the stars. Are they twinkling because you're looking at them? Or do they twinkle even when no one's around? Quantum mechanics suggests that observation isn't passive. It plays an active role in shaping reality. Some scientists argue that a conscious observer may be needed to collapse the many possibilities into one solid outcome. This leads to an even bigger question. Is consciousness part of the universe's design? Is the mind not just something in the universe, but something that helps form it? Many worlds, more used than you think now, Let's imagine a different kind of answer to this puzzle. Instead of the universe picking one outcome when a quantum event happens, what if all outcomes happen, but in different parallel worlds? This idea is called the many worlds interpretation. Every time a quantum event occurs, like the cat being alive or dead, the universe splits. In one version, the cat lives. In another, it dies. There's a universe where you chose tea, and one where you picked coffee. There's even one where you became an astronaut or never existed at all. It sounds like science fiction, but many serious physicists consider it possible. If it's true, there may be infinite versions of you, living different lives in different realities. Does time really flow? When you look at your watch ticking, you assume time is moving forward. But in quantum mechanics, time isn't as straightforward. The laws that govern particles don't care whether time is moving forward or backward. Some experiments even suggest that particles might influence the past, or that the future is already written. So maybe time isn't a straight line, but more like a block where past, present, and future all exist at once. We just experience it like a film, frame by frame. Reality or illusion? Have you ever had a dream that felt real? And when you woke up, it took a moment to remember what was real and what wasn't. Quantum physics makes us ask the same thing about everyday life. Some scientists believe the universe might be a simulation, like a giant computer program made of information. What we see and touch could be like pixels on a screen, just data being processed. If this is true, then the universe isn't physical at all. It's digital, and reality is just the result of code running somewhere we can't see. Even if that idea sounds extreme, quantum mechanics constantly reminds us that what we consider solid and certain is actually fuzzy and unpredictable. Consciousness and the brain. Are we quantum beings? One of the most debated questions is whether the brain itself works on quantum principles. Some scientists propose that tiny structures inside our brain cells, called microtubules, might be where consciousness arises through quantum processes. If that's true, then we are not just observing the quantum world, we are part of it. Our thoughts, memories, and awareness could be quantum effects playing out inside our skulls. Imagine that for a second. Every dream, every emotion, every memory could be the result of quantum waves dancing inside your brain. What happens when we sleep? And now that you're lying down, calm and still, maybe you're wondering, what happens to reality when you close your eyes? Does the universe keep spinning just the same? Or is reality pausing for you, waiting for your mind to wake up again? As your body slows down and your brain shifts into dream mode, perhaps you are slipping into another version of the universe, a world ruled entirely by probabilities and possibilities. A quiet goodbye from a strange world. Quantum mechanics doesn't just give us answers, it gives us better questions. It teaches us that reality might not be what it seems, that our thoughts may shape the universe, and that the world is far more mysterious than we can ever fully understand. As you drift into sleep, let the paradoxes carry you gently. Somewhere, in a far-off version of this world, you may already be dreaming, or waking, or thinking about cats in boxes and stars that twinkle because you smiled at them. Quantum mechanics paradoxes: to fall asleep, to close your eyes, and imagine a universe where the rules of reality are constantly shifting. A universe where particles can be in two places at once, and where time may not even be real. What if I told you that our universe, the one we experience every day, was born from a moment so bizarre that it seems impossible to understand? The story of the universe's beginning is filled with paradoxes and mind-bending concepts that challenge everything we think we know. Let's take a deep breath, settle into this mystery, and drift into the strange quantum world. Tonight, we will explore paradoxes in quantum mechanics that defy our understanding. paradoxes that exist not in some distant galaxy, but in the very fabric of reality around us. So relax, close your eyes, and let your mind wander as we embark on a journey to the origins of the universe and beyond what came before the Big Bang. Imagine a time when the entire universe, everything that exists, was crammed into an infinitesimally small point, denser than anything you can imagine. This point is what we call a singularity, a state where the laws of physics as we know them break down entirely. In the singularity, time and space were meaningless. There was no before, because time itself didn't exist. It's difficult to wrap our minds around this concept. We are creatures living in time. Everything happens in the past, present, and future. But at the singularity, everything we know about the world simply disappears. Scientists believe that the universe exploded into being from the singularity about 13.8 billion years ago in an event known as the Big Bang. But what happened before this moment? Normally, we think of the universe as having a beginning, a moment when everything came into being. But quantum mechanics asks us to consider an alternative. What if there was no beginning at all? What if time, in the way we understand it, is just an illusion? This thought alone can be overwhelming, but it opens up fascinating possibilities. Quantum mechanics, the strange dance of particles in the world of quantum mechanics. Reality is a dance of uncertainty. Imagine a tiny particle, too small to see, and try to picture its exact location and velocity. In classical physics, these two properties would be fixed, known. But in the quantum world, things are very different. According to the famous Heisenberg uncertainty principle, the more precisely we try to measure one property, the less precisely we can measure the other. In essence, particles can exist in multiple states at once. They can be in two places simultaneously, and they can even influence each other instantly, regardless of how far apart they are. Take the concept of superposition. This idea suggests that particles can exist in multiple states at the same time. For example, an electron in an atom can exist in multiple energy levels until it is observed. Once we look at it, the particle decides where it should be. This is not just science fiction. It's something that has been proven experimentally. Particles are strange, unpredictable, and their behavior cannot always be explained by the rules of classical physics. What if our entire universe is in some kind of quantum superposition, where multiple possibilities are unfolding simultaneously? Could there be parallel universes, each following a different version of reality, all existing side by side but never interacting with one another? These are some of the questions that physicists are trying to answer. The quantum leap, spontaneous, creation of the universe. Let's pause for a moment and think about how the universe might have come into being. One of the most fascinating ideas is that the universe was born out of a quantum fluctuation. Quantum fluctuations are tiny, random changes in energy that occur in empty space. These fluctuations happen all the time in the quantum world, and scientists believe that one such fluctuation may have triggered the birth of the universe. The concept is wild, isn't it? According to this theory, the universe could have come from nothing. In the quantum world, nothing doesn't mean emptiness. Instead, it's filled with energy that fluctuates constantly. Some scientists believe that the universe emerged from one of these random energy fluctuations. If that's true, it means that the universe could have come from absolutely nothing, no space, no time, just pure energy. But here's the paradox. Most quantum fluctuations lead to the creation of virtual particles that flicker in and out of existence in the blink of an eye. But somehow, one fluctuation led to the creation of an entire universe that's still expanding 13.8 billion years later. Why did this fluctuation persist? Why didn't it simply disappear like most quantum events? This question has kept physicists guessing for years, And the answer may be stranger than we can imagine. The Big Bounce. A universe in cycles now. Let's step back and consider a different idea. What if the Big Bang wasn't the beginning at all? What if the universe goes through cycles of birth, death, and rebirth? This concept is known as the Big Bounce. In this model, the universe expands for billions of years, then slows down, contracts into a dense state, and finally explodes into a new expansion. This cycle could repeat infinitely. In the Big Bounce theory, the Big Bang is not the ultimate beginning of the universe, but rather just one of many cycles. In this view, there's always been a universe, just not the one we experience now. The universe we know could be the result of a previous universe collapsing and then re-expanding. But here's the paradox. If the universe has always existed in this cycle, then what triggered the first expansion? What started the first Big Bang? These are questions that don't have clear answers, but they do suggest that the universe could be much older than we think. Instead of a single beginning, the universe might be part of an eternal cycle of expansion and contraction. The multiverse. Is our universe just one of many? One of the most mind-boggling ideas in modern physics is the concept of the multiverse. Imagine that our universe is not the only one. What if there are infinite universes, each with its own physical laws, each slightly different from the other? In this vast cosmic landscape, each universe would exist independently, with no interaction between them. This idea comes from the theory of eternal inflation, which suggests that after the Big Bang, the universe didn't just expand in a single burst. Instead, different regions of space-time inflated at different rates, creating bubbles, each one a separate universe. Some of these universes could be similar to ours, while others could have entirely different physical laws, such as different numbers of dimensions or different constants of nature. If the multiverse theory is true, then the universe we know may be just one bubble in an infinite sea of bubbles. But this raises a deep paradox. If there are infinite universes, how can we ever know anything about the others? What does it mean to live in a universe if there are so many others, each with its own version of reality? String theory, the hidden dimensions of reality. Now, let's look at another theory that could explain the origins of the universe. String theory. This theory suggests that the fundamental building blocks of the universe are not particles, but tiny vibrating strings. These strings are so small that they are invisible to our current technology, but they may be the key to understanding the universe at its most fundamental level. String theory also proposes that there are extra dimensions of space dimensions, beyond the three we experience in everyday life. These dimensions could be hidden from us, but they may be crucial to understanding the behavior of the universe. One idea is that the Big Bang was caused by the collision of two of these extra-dimensional brains, short for membranes. The universe we see today could be the result of one brain colliding with another in a higher dimensional space. If this theory is true, it means that the Big Bang wasn't just a local event. It was a cosmic collision that happened in a much larger, multi-dimensional space. But this also raises more questions. What are these higher dimensions? What other forces exist in these dimensions? And could there be other universes that are completely hidden from our perception? The nature of time. Is time real? One of the strangest ideas in quantum gravity is that time itself may not be real. In this view, time is not a fundamental property of the universe, but an emergent phenomenon. Just like temperature is a result of the motion of particles, time may be a result of deeper, more fundamental laws of nature that we don't yet understand. If time isn't fundamental, then asking what happened before the Big Bang may not make sense. In this picture, time could be something that emerges from a more fundamental layer of reality, much like how the temperature of a gas emerges from the movement of molecules. But what does that mean for our experience of time? If time isn't real, How do we understand our past, present, and future? The endless search for answers as we drift into sleep. It's important to remember that we are only scratching the surface of these profound mysteries. What happened before the Big Bang? How did the universe come into being? Is time even real? These questions remain open, and scientists continue to search for answers. But one thing is certain: the universe is full of wonders, paradoxes, and mysteries that we have yet to comprehend. Perhaps in time, we'll uncover the true nature of the cosmos, or perhaps some mysteries will always remain just beyond our reach. But for now, let your mind relax and wander through the strange, beautiful world of quantum mechanics. The universe may be far stranger than we could ever imagine, and that's what makes it so fascinating. Quantum mechanics paradoxes to fall asleep, to welcome to the mysterious and strange world of quantum mechanics. This is a place where the normal rules of reality don't apply, where time, space, and even logic become slippery and uncertain. Tonight, we're going to explore one of the most fascinating paradoxes in quantum physics, the Double-Slit Experiment, a thought experiment that not only challenges our understanding of physics, but also our very perception of reality itself. So sit back, relax, and let's drift off into the strange world where nothing is quite as it seems. Introduction to Quantum Mechanics and the Double-Slit Experiment. Let's begin with a basic question. What is reality? In our everyday lives, reality seems solid and predictable. We know that when we drop an object, it falls to the ground. We understand that light moves in a straight line, and we know how to measure time in seconds, minutes, and hours. But in the world of quantum mechanics, these familiar concepts begin to break down. And nowhere is this more evident than in the Double-Slit Experiment. The Double-Slit Experiment is one of the most famous thought experiments in physics, and it has baffled scientists since it was first conducted in the 19th century. The experiment involves firing particles, like electrons or photons, at a barrier with two slits in it. The particles then pass through the slits and hit a screen, where they create a pattern. Sounds simple, right? But here's the twist. The particles behave differently depending on whether or not we observe them. When no one is watching, the particles create an interference pattern on the screen. This pattern is typical of waves, not particles. It's as if the particles are behaving like waves of light, spreading out and interfering with each other. But when we try to measure which slit the particle passes through, the interference pattern disappears. Instead, the particles behave like tiny solid objects, passing through one slit or the other, and creating two distinct patterns on the screen. At first glance, this seems impossible. How can particles behave like waves and like particles at the same time? This is where quantum mechanics gets its reputation for being strange and paradoxical. It's as if the act of observation itself is changing the nature of the particles. The paradox of wave-particle duality. This strange behavior is known as wave-particle duality, and it forms the heart of the mystery behind the Double-Slit Experiment. In the classical world, we're used to thinking of objects as either waves or particles. A wave is something that spreads out, like water rippling in a pond, while a particle is a solid object, like a tiny ball. But in the quantum world, particles can behave like both at once. This paradox challenges everything we know about the nature of reality. Imagine, if you will, that you are standing by the shore of a peaceful lake. You drop a stone into the water, and ripples begin to spread out across the surface. These ripples behave like waves, interacting with each other, canceling out, or amplifying one another. Now imagine that, at the same time, you drop a stone at exactly the same point in the lake. You would expect to see the stone sink into the water, right? It behaves like a particle. But here's where quantum mechanics takes a turn. In the Double-Slit Experiment, when we are not looking, particles behave like the ripples on the lake. They seem to spread out and interfere with each other, just like waves do. But when we try to measure which slit they go through, they behave like stones, acting solid and predictable. This dual nature of matter acting as both waves and particles forces us to rethink everything we know about the world. The observer effect. Reality depends on observation now. Let's take this paradox one step further. It's not just that. The particles behave differently when we observe them. The very act of observing them creates the reality we experience. This is known as the observer effect. Imagine a car driving down a road. If you're watching it, the car stays on the road, driving from one point to another. But if you look away for a moment, something strange happens. The car might disappear or change direction. It's as if the car's reality only exists when you're looking at it. This is a simplified version of what happens at the quantum level dot in the quantum world. Particles only choose a position or state when we observe them. Before observation, they exist in a state of probabilities, as if they're spread out across many possibilities at once. But the moment we look at them, when we measure them, they collapse into a single state, just like the car on the road, and behave in a predictable way. The observer effect suggests that reality itself is not fixed, but instead, it depends on the act of observation. The uncertainty principle, limits of knowledge, but it gets even more perplexing. Not only does observation change the behavior of particles, but there are also limits to what we can know about them. This is described by Heisenberg's uncertainty principle, one of the fundamental principles of quantum mechanics. The uncertainty principle states that we cannot know both the position and the momentum of a particle at the same time with absolute certainty. Imagine trying to take a photograph of a fast-moving car. The faster the car moves, the less precisely you can measure its position. Likewise, the more precisely you measure the car's position, the less you can know about how fast it's going. This is similar to how quantum particles behave. The more we try to measure one property, say, the particle's position, the less we know about its other properties. Like its speed or energy dot in the quantum world, this uncertainty isn't a limitation of our tools or methods. It's a fundamental feature of reality itself. Particles don't have definite positions or velocities until we measure them. They exist in a cloud of probabilities, and only by interacting with them do we force them to choose a specific state. Quantum superposition. Being in two places at once, if the idea of particles being in multiple states at once wasn't strange. Enough, there's another paradox that blows our minds: quantum superposition. This is the idea that particles can exist in multiple states simultaneously. In other words, a particle can be in two places at once, or it can have multiple possible energies at the same time. One of the most famous demonstrations of this paradox is Schrödinger's cat, a thought experiment designed by physicist Erwin Schrödinger. In this experiment, a cat is placed in a sealed box with a device that has a 50% chance of killing the cat by releasing poison. According to quantum mechanics, until we open the box and observe the cat, it exists in a superposition of both alive and dead states at the same time. Only when we observe the cat does it collapse into one definite state, alive or dead. While this may sound ridiculous, quantum mechanics suggests that particles behave in much the same way. They can exist in multiple states all at once until we observe them. This strange behavior highlights the radical difference between our everyday experience and the quantum world. Quantum, entanglement, spooky action at a distance, but quantum mechanics doesn't stop at superposition. It also introduces us to the concept of quantum entanglement, which Albert Einstein famously called spooky action at a distance. In entanglement, particles that are separated by vast distances can still affect each other instantaneously. When two particles become entangled, their states become linked, so that even if they are far apart, changes to one particle will instantly affect the other. no matter the distance between them. Imagine two dice thrown across a room. If you roll one die, the other die somehow knows what number came up, and it rolls the exact same number at the same time. Entangled particles behave in this way. If one particle's state changes, the other particle's state will change instantly, even if they are light years apart. This phenomenon seems to defy the speed of light and our understanding of how information can travel. And yet, experiments have repeatedly confirmed that quantum entanglement is real, the mysterious nature of reality. So, what does all of this mean? As we explore these quantum paradoxes, we find ourselves confronted with a world that defies logic and reason. Reality is not as fixed or predictable as we once thought. It's a place where particles can be in two places at once, where observation creates the reality we experience, and where the very act of measuring something changes its outcome. But these paradoxes aren't just theoretical. They're real, and they're shaping the way we understand the universe. From quantum computing to the nature of consciousness, quantum mechanics is changing our view of the world in profound ways. And as we continue to explore this strange realm, we may find that the lines between the observer and the observed, between the mind and the universe, are not as distinct as we once believed. As you drift off to sleep, remember, the world around you is full of mysteries, and the deeper we look, the stranger it becomes. In the quantum realm, reality is not fixed, fluid, and it's shaped by observation itself. Sweet dreams in a world where anything is possible. Quantum mechanics paradoxes to fall asleep to the night sky is vast and endless, filled with stars that have burned for billions of years. Their light reaches us from distances so far that our minds struggle to grasp their enormity. But as we gaze up at this cosmic sea, we are not only looking at a collection of stars. We are witnessing a universe governed by laws that baffle even the brightest minds. Quantum mechanics, the study of the smallest particles that make up everything, is a world where the rules of logic and reason do not always apply. The paradoxes that arise in this strange realm force us to question the very nature of reality. These paradoxes are not just theoretical curiosities. They are fundamental to understanding the universe and our place within it. In tonight's journey, we'll explore some of the most perplexing paradoxes in quantum mechanics, ones that challenge our sense of what's possible and stretch the limits of our imagination. Let us begin with the double-slit experiment, which has puzzled scientists and philosophers alike for centuries. In its simplest form, the experiment involves firing tiny particles like photons toward a barrier with two slits. If the particles behave like classical objects, they should pass through either one slit or the other and create two distinct lines on a screen behind the barrier. However, when no one is observing the experiment, the particles behave differently. They don't simply pass through one slit or the other, but rather behave like waves, creating an interference pattern. This pattern suggests that the particles pass through both slits at the same time, existing in a state of superposition. It's as if the particles are in two places at once. But when we observe the particles, they collapse into a single state, behaving like regular particles. This paradox leads to a troubling question. Does our act of observing the world influence its behavior? Are we somehow altering the reality we are trying to understand just by looking at it? This question of observation and its impact on reality is at the heart of the observer effect, which is another strange and perplexing aspect of quantum mechanics. Imagine you're observing a quantum particle, and as you measure it, its behavior changes. The very act of observing seems to force the particle to behave in a particular way. But why? Why does the simple act of looking cause such a dramatic shift in what the particle does? And more intriguingly, does it mean that the universe is somehow waiting for us to observe it before it becomes real? This idea is both fascinating and unsettling. leaving us to wonder whether the world exists as we perceive it, or whether it exists in an undefined state, waiting for our observation to snap it into existence. Next, let us move on to Schrödinger's cat, a thought experiment that amplifies the absurdity of quantum mechanics. Schrödinger, a physicist, proposed an idea to illustrate the paradoxes of quantum mechanics. Imagine a cat placed inside a sealed box. Alongside the cat, there is a radioactive atom with a 50% chance of decaying within an hour. If the atom decays, a vial of poison is broken, killing the cat. If the atom does not decay, the cat remains alive. According to quantum theory, the atom exists in a state of superposition. It is both decayed and not decayed at the same time. As a result, the cat is both alive and dead simultaneously, as long as the box is sealed and we have not observed it. It is only when we open the box and observe the cat that it decides to be either alive or dead. This paradox challenges our understanding of reality itself. How can something be in two states at once? And more importantly, what does this say about our perception of life and death? What happens when reality itself refuses to take a single, defined form? One of the most baffling aspects of quantum mechanics is the Heisenberg uncertainty principle. It states that it is impossible to simultaneously know both the exact position and the exact momentum of a particle. The more precisely we measure one, the less precisely we can measure the other. At first glance, this may seem like a flaw in our instruments, but it's not. It's a fundamental property of the universe. This principle suggests that the universe at the quantum level is inherently uncertain, that there is no such thing as absolute precision. The implications are profound. If the universe itself is built on uncertainty, then perhaps nothing is truly predictable, even in principle. This idea clashes with our classical understanding of the world, where we can, in theory, predict the behavior of objects with great accuracy. But at the quantum level, the universe seems to resist our attempts at full understanding. It reminds us that the more we try to understand the universe, the more it slips through our fingers. Quantum entanglement is another mind-bending phenomenon that challenges our intuitions. Imagine two particles separated by vast distances, yet mysteriously linked. If something happens to one particle, the other particle's state is immediately affected, regardless of the space between them. This connection, known as entanglement, occurs instantly, even if the two particles are light years apart. Einstein referred to this as spooky action at a distance, and it seems to defy the conventional rules of space and time. How can particles communicate faster than the speed of light? And what does this mean for our understanding of the universe? It suggests that our conventional notion of space and time is not as fixed as we might think. Could this be evidence of a deeper, hidden connection between all things in the universe? A connection that transcends the limits of space and time? As we delve further into the strange world of quantum mechanics, we come to quantum tunneling, a phenomenon that seems to defy the very laws of physics. In classical mechanics, particles need a certain amount of energy to overcome a barrier. If they don't have enough energy, they simply cannot pass through. But in quantum mechanics, particles can tunnel through barriers, even if they don't have enough energy to do so. It's as though they can bypass the laws of physics, moving through obstacles that should, by all accounts, be impassable. This paradox raises questions about the very nature of reality. What if we could, metaphorically, tunnel through the walls of our own lives, bypassing the obstacles that hold us back? What if the universe itself is full of hidden paths, waiting to be discovered? Quantum tunneling suggests that the rules we take for granted are not as rigid as we think, and that the universe may be far more malleable than we realize. One of the most fascinating and bizarre implications of quantum mechanics is its relationship with parallel universes. The idea of parallel universes, or the multiverse, suggests that there are an infinite number of universes, each with its own version of reality. In some of these universes, events might unfold in slightly different ways, or perhaps completely differently. If the many worlds interpretation of quantum mechanics is true, every time a quantum event occurs with multiple possible outcomes, the universe splits, creating a new universe for each possible outcome. This means that for every decision we make, there could be an alternate universe where we made a different choice. The thought that our universe might be just one of an infinite number of universes is both awe-inspiring and deeply unsettling. Are we truly the center of our own reality? Or are we just one version of ourselves, living in one of countless worlds? These paradox, entanglement, superposition, the observer effect, tunneling are not just abstract concepts. They have real-world implications. The quantum computer, for example, takes advantage of these strange phenomena to solve problems that are currently impossible for classical computers. Quantum computers use qubits, which, unlike classical bits, can be in multiple states at once. This allows them to perform calculations at unimaginable speeds. But the very nature of quantum computers is itself paradoxical. How can we use a system that is built on uncertainty and superposition to calculate answers with such precision? It's as if we are using the very chaos of the quantum world to create order in our technological systems. And yet, despite all the uncertainty and the paradoxes, there is a certain beauty in quantum mechanics. It reminds us that the universe is far more complex, mysterious, and interconnected than we could ever imagine. The universe is not a static machine operating according to predictable laws. It is dynamic, fluid, and full of strange, unpredictable behaviors. These paradoxes are not just anomalies. They are glimpses into a deeper, more fundamental truth about the nature of reality. The universe is not a set of isolated events, but rather a vast, interconnected web of possibilities, each one influencing the next in ways we cannot yet fully understand. As we lay down tonight, let these paradoxes lull us into a peaceful slumber. Let them remind us that the universe, with all its mysteries and uncertainties, is a place of infinite wonder. We may never fully understand it, but perhaps that's the beauty of it all. The journey of discovery never ends, and as we drift off to sleep, we can rest knowing that tomorrow we will wake up to another day of exploration, curiosity, and the pursuit of knowledge. Imagine a world where the very fabric of reality seems to bend and twist, where the rules we rely on in our everyday lives no longer apply. A world so strange and so deeply perplexing, it seems almost like a dream, yet it is the reality that governs the universe at its most fundamental level. This world exists not in the realms of fiction, but in the mysterious realm of quantum mechanics. While we may think we understand reality, the bizarre paradoxes of quantum mechanics challenge our assumptions and offer a view of the universe that's far stranger than we could ever have imagined. Tonight, as you close your eyes and drift off into slumber, let your mind wander into the quantum realm, a place where particles behave in ways that defy reason, where light is both a particle and a wave, and where our very act of observing something can change its reality. The paradoxes of quantum mechanics might just be the key to unlocking the deepest mysteries of the universe, and maybe even the mysteries of your own mind, the duality of light, particle, or wave. In the world of quantum mechanics, light is both a wave and a particle. This seemingly contradictory nature of light is one of the most famous quantum paradoxes, known as wave-particle duality. When scientists first discovered this strange behavior, they were forced to reconsider everything they thought they knew about light. Could it really be both? Imagine yourself standing in a dark room with a small slit in the wall. You shine a beam of light through that slit, and instead of just illuminating a single point on the opposite wall, the light spreads out in waves, creating an interference pattern like ripples in a pond. This behavior shows light acting as a wave, but now place a detector at the slit to measure the light. When you do, light behaves like a particle, traveling through the slit and creating a single focused point on the wall. So which is it, a wave or a particle? In the quantum world, this paradox doesn't have a simple answer. The truth is, light is neither fully one nor the other. It's both, depending on how we observe it. The very act of observation influences the behavior of the light, as if the universe itself is playing a game of hide and seek, only revealing part of its nature when we decide to look. This paradox reminds us of the limitations of our understanding and how the very act of observing the world shapes our reality. As you lie in bed, drifting into sleep, think about the duality of light. How many aspects of your life are both at once uncertain, shifting, changing, depending on where you stand and how you look at them? Are you, too, a mix of opposing forces, balancing between many versions of yourself, just like light? The strange case of quantum superposition. Imagine you are in a room with a door that leads to two possible worlds, one filled with bright light and joy, and the other with darkness and sorrow. In the classical world, you'd only be able to choose one path, stepping into either the light or the darkness. But in the quantum world, something strange happens. You step into the room, and both doors are open at the same time. You are, in fact, not choosing one or the other. You are both in the light and in the darkness at once. This paradox, known as quantum superposition, is the idea that a particle can exist in multiple states simultaneously until it is observed. In the famous thought experiment known as Schrödinger's cat, a cat inside a box can be both alive and dead at the same time, existing in a superposition of states until the box is opened and the cat is observed. Until the act of observation occurs, the cat is neither alive nor dead. It is in a state of quantum indeterminacy. Now, imagine your own thoughts and decisions. In your waking life, you often feel torn between multiple options. Should you take that job, move to that city, or stay where you are? In the quantum world, the multiple possibilities exist simultaneously, each one a possible version of you. But only when you make the decision, when you observe and act, does the superposition collapse into one reality. Quantum superposition reminds us that, in a sense, life itself could be a wave of infinite possibilities. You may be living in a superposition of potential outcomes, and only when you make a choice does the world settle into a singular reality. As you close your eyes, imagine all the possible lives you could lead, each one a quantum possibility, waiting to be explored, as if the universe is holding its breath, waiting for your next move. The uncertainty principle, knowing less to know more. The more you try to measure something, the less you know about it. This is the essence of Heisenberg's uncertainty principle, which states that there are limits to how precisely we can know both the position and momentum of a particle at the same time. The act of measuring one property of a particle disturbs the other, making it impossible to know both with certainty. In the classical world, we believe that if we measure something precisely, we'll know everything there is to know about it. But in the quantum world, the very act of measurement changes the outcome. This is a deep paradox. The more we try to understand the universe, the more we realize how little we actually know. Take a moment as you lie in bed to reflect on this paradox. How often do you find yourself trying to control every detail of your life, measuring every step you take, yet feeling like the more you focus on the details, the less you understand the bigger picture? The uncertainty principle reminds us that there is beauty and wisdom in uncertainty, and sometimes letting go of control is the key to understanding. Quantum entanglement. Spooky action at a distance. One of the most mind-boggling aspects of quantum mechanics is the phenomenon of quantum entanglement. When two particles become entangled, they are linked in such a way that the state of one particle is immediately connected to the state of the other, regardless of how far apart they are. If you separate the particles by vast distances, thousands of miles or more, measuring one particle's state will instantly reveal the state of the other, faster than the speed of light. This phenomenon baffled even Albert Einstein, who famously referred to it as spooky action at a distance. According to classical physics, information cannot travel faster than light. Yet quantum entanglement seems to defy this limit, suggesting that the particles are connected in some unknown, non-local way. What if our minds are entangled with the universe in ways we don't yet understand? What if, just like these particles, our thoughts and actions are interconnected in a way that transcends space and time? As you drift into sleep, think about the moments in your life when you felt an inexplicable connection to someone, as if their thoughts were intertwined with your own. Could it be that, on a quantum level, we are all entangled, each action reverberating across the universe? A measurement problem. Does reality exist without us? One of the greatest questions raised by quantum mechanics is whether reality exists when we're not looking at it. In classical physics, objects exist independently of whether we observe them. But in the quantum world, particles exist in multiple states simultaneously until they are measured. When no one is watching, the universe remains in a state of potential. Only when we observe something does it collapse into one definite state. This brings up a profound philosophical question. If no one is watching, does reality truly exist? The measurement problem forces us to reconsider the very nature of existence. Is reality something external that we perceive, or is it something that is created by our consciousness? Are we co-creators of the universe, shaping it with our awareness? As you fall asleep, think about how you shape your own reality. Every thought you have, every choice you make, brings the world into focus. Could it be that the universe itself, like the particles in quantum mechanics, exists only because we observe it? Does reality need us to exist just as much as we need reality to shape our experience? The quantum realm as a dream world. Quantum mechanics forces us to face a mind-bending paradox. The universe is not as it seems. It is not a simple, predictable machine that we can measure and control. Instead, it is a dynamic, mysterious world where the rules we rely on in our everyday lives break down, and the lines between the real and the imaginary blur out as you drift deeper into sleep. Let your mind wander into the quantum realm. Embrace the paradoxes, the uncertainty, the entanglement, the strange duality of reality. The quantum world reminds us that there is much more to existence than we can see, much more than we can understand. And perhaps, just as in the quantum world, your dreams too exist in multiple states, shifting, changing, and expanding into infinite possibilities, waiting for your consciousness to bring them into focus. May you drift into a peaceful sleep, where the boundaries of reality and imagination dissolve, and you awaken in a world where the strangest of paradoxes are simply part of the beautiful mystery of existence. A peaceful journey into the infinite universe. Have you ever laid awake at night, staring at the ceiling, thinking about the vastness of the universe? The stars twinkling above, the endless night sky stretching far beyond what we can see with our eyes. There's something deeply mysterious about the universe. Even when we understand more, we realize that there's so much more we don't know. One of the greatest mysteries of all is the universe's very fabric, governed by the strange and beautiful rules of quantum mechanics. Let's drift into a peaceful sleep tonight with a journey into the fascinating paradoxes of quantum mechanics. These ideas, while puzzling and hard to grasp, are also what make our universe a place of endless wonder. Relax, let go of your worries, and let the paradoxes of the quantum world gently guide you toward sleep. The quantum universe. Reality is not what it seems. Imagine you are standing in a quiet room surrounded by objects you can see and touch. In the world we experience, things seem solid, stable, and predictable. However, the world at the quantum level, the world of the tiniest particles that make up everything around us, is anything but predictable dot in the quantum realm. Reality isn't. As it seems, particles, the basic building blocks of matter, don't behave in a way we can easily understand. They can be in multiple places at once, travel through barriers that should be impossible to pass, and even affect each other instantly. No matter how far apart they are, this strange behavior of particles defies all our common sense. In the quantum world, particles are not located at just one place or moving in one direction. They can be in many places, traveling in different directions at the same time. This is called quantum superposition. Particles exist in multiple states until we observe them. It's only when we look that they choose one state. Imagine being in two places at once or having multiple paths to take. This paradoxical idea is central to understanding quantum mechanics. The observer's paradox. What happens when we look? Here's where things start to get even more confusing. In the quantum world, the act of observing something changes what it is. This is known as the observer effect. When we observe a quantum particle, like an electron, it decides which state to be in. Before we observe it, the particle is in a superposition in multiple states at once. This raises a perplexing question. How can something exist in multiple states if no one is looking? And what happens when we look? How does observation change? What we see? In our daily lives, we expect the world to behave in predictable ways. But at the quantum level, just by observing, we change the outcome. Imagine looking at the stars. The moment you focus on a star, it no longer exists in multiple places at once. It's just one point of light in the sky. But what if, in a way we don't understand yet, all the stars are constantly existing in multiple forms, waiting for someone or something to look at them? Quantum entanglement. Instantaneous connections across vast distances now. Let's explore another fascinating paradox, quantum entanglement. Entanglement is one of the most mind-boggling concepts in quantum mechanics. It tells us that particles can become linked or entangled in such a way that no matter how far apart they are, a change in one particle will instantly affect the other. This happens even if the particles are on opposite sides of the universe. Imagine two particles, one in your hand and the other on the far side of the universe. When you change the state of one particle, the other particle will immediately mirror the change, even though there's no time for information to travel between them. This is called spooky action at a distance. It seems impossible, doesn't it? How can particles communicate instantly over such vast distances? And yet, this phenomenon has been proven in experiments and is a real paradox in the quantum world. Entanglement also challenges our understanding of space and time. In our classical world, information takes time to travel. But in the quantum world, entangled particles seem to bypass that limit, connecting in ways we can't yet explain. The Double-Slit Experiment, a mystery in plain sight. Let's travel further into the world of quantum paradoxes with the famous Double-Slit Experiment. This experiment involves shining light or particles through two slits in a barrier and then observing the pattern that emerges on the other side. In our everyday world, we would expect the light or particles to behave like tiny balls passing through one slit or the other and creating two distinct patterns on the other side. But that's not what happens. Instead, light and particles behave like waves and create an interference pattern, as if they pass through both slits simultaneously. It's as if they are spreading out, creating waves of probability. What's even stranger is that if we observe which slit the particles go through, they behave like particles again, creating two distinct patterns. But if we don't observe them, they behave like waves, This paradox shows us that at the quantum level, particles don't behave as solid, fixed objects. They behave more like waves, existing in a cloud of probabilities. The simple act of observation forces them into a defined state, revealing the true power of the observer effect. The particles exist in multiple possibilities until we look. And when we do, the universe chooses one of them. Quantum tunneling, breaking through barriers another. Quantum paradox involves quantum tunneling. Imagine a ball rolling toward a hill. Normally, it would need enough energy to climb the hill and pass over it. However, in the quantum world, particles can tunnel through barriers that would stop any object in the classical world. It's as if the ball never hits the hill at all, instead passing through it, appearing on the other side without ever crossing the top dot. This idea of particles passing through barriers, even seemingly impossible ones, has been observed in experiments. For example, in the sun's core, nuclear reactions occur through quantum tunneling, where particles pass through energy barriers that classical physics would say are insurmountable. It's a reminder that in the quantum world, limits are not always what they seem. Barriers can be bypassed. Paths can be found where there should be none. The uncertainty principle, embracing the unknown one. Of the most famous paradoxes in quantum mechanics is Heisenberg's uncertainty principle. This principle tells us that we can't know both the position and the momentum of a particle with absolute certainty. The more precisely we know one, the less precisely we can know the other. It's not just a matter of measurement errors. This is a fundamental limit of nature itself. Imagine trying to track the position and speed of a car. The more precisely you measure the car's position, the less you can know about its speed, and vice versa. In the quantum world, this principle doesn't just apply to cars. It applies to everything, from electrons to photons, the very building blocks of reality. It reminds us that there's a fundamental uncertainty at the heart of the universe. And no matter how much we learn, there will always be mysteries beyond our reach. Quantum physics and the nature of reality. As you drift into sleep, let these paradoxes swirl around you. The superposition of particles, the entanglement that connects everything, the double-slit experiment that reveals the strange nature of light, and the uncertainty principle that reminds us how little we truly know. These paradoxes are more than just abstract scientific concepts. They are a window into the true nature of the universe. A universe that is far more mysterious than we can fully comprehend. At the quantum level, reality is not solid, fixed, or predictable. It's a world of possibilities, probabilities, and uncertainty. Particles can be in multiple places at once, can influence each other instantly, and can pass through barriers that seem impossible. And yet, this is the very fabric of our universe. As strange and perplexing as it may be, it's the foundation upon which everything rests, from the stars above to the atoms in your body. Letting go of the mystery, as you relax, feel the weight of the mystery ease away. Quantum mechanics isn't something we need to fully understand. In fact, the more we try to understand it, the more it invites us to embrace the unknown. Just like the quantum particles, we don't need to know everything to be at peace. Sometimes, the greatest wisdom comes from letting go of the need for answers and allowing the mystery to simply be. Tonight, as you drift into sleep, think of the quantum paradoxes as a lullaby for your mind, gentle, soothing, and full of wonder. Let the strange beauty of the quantum world lull you into a deep, peaceful rest, knowing that even in the most puzzling corners of the universe, there is an unexplainable harmony. The universe is vast, mysterious, and at times unfathomable. In the pursuit of understanding the fundamental nature of reality, scientists have uncovered astonishing paradoxes that reveal the world behaves in ways that contradict our intuition. These paradoxes come from the realm of quantum mechanics, an area of science that challenges everything we think we know about how the universe works. Quantum mechanics allows us to ask questions that stretch the limits of imagination. As we venture through some of these mind-bending concepts, let your mind wander, and perhaps they may lull you into peaceful slumber at the Double-Slit Experiment, a world of uncertainty. One of the first and most famous paradoxes in quantum mechanics is the Double-Slit Experiment. Imagine shining a beam of light through two slits onto a screen. If you don't observe the light, it behaves like a wave, and you get an interference pattern multiple light bands on the screen. But when you observe the light, it acts like particles, and you see only two bands. This experiment demonstrates the dual nature of light and matter. It shows that particles, like electrons, can behave both as waves and particles, depending on whether they are being observed. The paradox here is profound. When we aren't looking, particles behave like waves spread out over space. But the moment we observe them, they collapse into a single position, behaving as particles. This suggests that the universe is not as fixed as we think. Observation, it seems, plays a critical role in shaping the outcome of events. Imagine the universe as a giant stage where every act is influenced by the audience. As strange as it sounds, quantum mechanics hints that the world may not fully exist in a fixed state until we observe it. It is as if the very act of looking is enough to bring a particular reality into being. Schrödinger's cat, a paradox of life and death. Another mind-boggling paradox comes from Schrödinger's cat, a thought experiment designed to illustrate the strange and counterintuitive world of quantum mechanics. In this scenario, a cat is placed inside a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers the release of poison, killing the cat. If the atom doesn't decay, the cat stays. Alive. Quantum mechanics says that until you open the box and observe the cat, the atom is both decayed and not decayed, and the cat is both alive and dead at the same time. This is known as superposition, the idea that quantum objects can exist in multiple states simultaneously. The paradox here is not just about a cat being alive and dead, but about the very nature of reality. It challenges our fundamental understanding. Can something truly be in two contradictory states at once? Is reality only real when we observe it? Schrödinger's cat may be a hypothetical scenario, but it illustrates a core concept of quantum mechanics that before we measure something, it exists in all possible states. It is only upon observation that the cat's fate, and thus reality itself, is decided. Quantum entanglement, instantaneous connections across space. Another strange and fascinating phenomenon is quantum entanglement. Entanglement occurs when two particles become linked in such a way that the state of one particle is directly tied to the state of another, no matter how far apart they are. The moment you measure the state of one particle, the state of the other particle is instantly determined, even if it's light years away. This paradox seems to defy the laws of physics, particularly Einstein's theory of relativity, which states that no information can travel faster than the speed of light. Yet, entangled particles behave in exactly this way, violating what we thought were the fundamental rules of nature. What's even more baffling is that this connection between entangled particles appears to happen instantaneously, without any time delay. This suggests that at a quantum level, space and time may not behave the way we think they do. The particles are somehow aware of each other, and their states are interdependent, even across vast distances. It's as if the universe itself is an interconnected web, where everything is linked, whether we can see it or not. Could quantum entanglement be the key to the future of communication? Could it one day allow us to send information across vast distances instantly? Though it seems impossible, entanglement is a proven phenomenon that challenges our understanding of the fundamental laws of nature. The measurement problem Observation creates reality in the quantum world. The act of measurement itself plays a crucial role in determining the state of a particle. Before measurement, a quantum object exists in a superposition of all possible states. But once we measure it, whether we observe its position, speed, or other properties, it chooses one of these states. The superposition collapses, and the particle assumes a definite state. This paradox, known as the measurement problem, raises a profound question. What role does the observer play in shaping reality? Does the universe exist as a collection of probabilities, with all possible outcomes unfolding simultaneously until we observe one? Or does the act of observing create reality itself, collapsing the wave of possibilities into a single definite outcome? The implications of this paradox go beyond quantum mechanics. If observation is what causes reality to choose its form, it challenges our traditional understanding of existence. Does the universe only exist when we are watching it, or is it independent of our observation? The measurement problem forces us to reconsider what we mean by real. The grandfather paradox and time travel, another paradox that stretches the limits of our understanding, is the grandfather paradox, which explores the concept of time travel. Imagine you could travel back in time and accidentally kill your grandfather before your parent was born. If your grandfather never had children, you would never have been born. But if you were never born, how could you have traveled back in time to kill your grandfather in the first place? This paradox raises profound questions about the nature of time. Does time unfold in a fixed, linear sequence, or can we change the past? If time travel were possible, would it create inconsistencies like this, leading to self-contradictory situations? Some physicists suggest that time travel may create alternate realities or timelines. When you alter the past, you might not change the original timeline, but create a new one that diverges from the original reality. Time travel remains a topic of intense debate, and while we have yet to discover the means to travel backward in time, the paradox itself shows how complex the concept of time truly is. It reminds us that time may not be as simple as it seems. Perhaps time, like everything else in quantum mechanics, is much more fluid and flexible than we realize. Quantum tunneling, the impossible journey in the classical world. If a ball rolls toward a hill and doesn't have enough energy to reach the top, it simply stops. However, in the quantum world, particles behave in strange ways. One of these phenomena is quantum tunneling, where particles can pass through barriers that they don't have enough energy to cross. Imagine a ball rolling toward a hill. If it doesn't have enough energy, it should be blocked by the hill. But in the quantum world, particles can sometimes tunnel through the hill, appearing on the other side without ever having enough energy to go over it. This seemingly impossible journey is a fundamental aspect of quantum mechanics, and it is crucial to many processes, including nuclear fusion in the sun and the function of certain electronic devices. Quantum tunneling challenges our classical understanding of how objects move and interact. It suggests that at the quantum level, the boundaries of possibility are much less rigid than we imagine. Particles, it seems, can sometimes defy the laws of classical physics, creating new possibilities and outcomes that seem impossible in our everyday experience. The arrow of time and entropy, one of the most perplexing paradoxes in physics, is the nature of time itself. We experience time as moving in one direction, from past to present to future. This progression is linked to the concept of entropy, the measure of disorder in a system. According to the second law of thermodynamics, entropy tends to increase over time, meaning that systems naturally evolve from order to disorder. But quantum mechanics presents a different picture. At the quantum level, particles don't always follow a smooth, predictable path. They can move backward in time, creating situations where entropy might not always increase. Could time, at its most fundamental level, be reversible? Could the arrow of time be an illusion created by the way we observe the universe? This paradox challenges our understanding of time as a one-way street. If entropy can decrease and time can flow backward at a quantum level, perhaps time itself is not as fixed as we believe. It is another reminder that the universe, at its most fundamental level, is full of mysteries that we have yet to fully grasp. As you drift off to sleep, these paradoxes will continue to swirl in your mind. The mysteries of quantum mechanics are vast, and though they seem to defy logic, they are the building blocks of our universe. Whether they offer insights into the deepest nature of reality or simply challenge our understanding, they remind us that the universe is full of wonders yet to be discovered. As you close your eyes and let your thoughts float, remember that in the quantum world, anything is possible, perhaps even dreams of worlds beyond our own. Let your mind wander through these mysteries and allow the unknown to guide you into a peaceful slumber. Quantum mechanics, often considered the strangest branch of science, has fascinated and baffled physicists for over a century. It's a field full of paradoxes, where the very rules that govern our world seem to break down. But in this script, we're going to explore these paradoxes in a soothing way. Let's embrace the mysteries of the universe and drift off into sleep, thinking about the deep questions of existence, where the line between what's possible and impossible becomes beautifully blurred. The wave-particle duality, a dance of contradictions. Imagine this. Light is both a wave and a particle. Yes, that's right, light behaves like a wave in some situations and like a particle in others. This strange duality was first demonstrated by Thomas Young in the 19th century, when he showed that light can create interference patterns, something only waves can do. But the mystery deepens when scientists tried to understand this more deeply with particles, like electrons. In an experiment, electrons were fired at a screen with two slits. When unobserved, they formed an interference pattern, just like light. But when observed, the electrons behaved as if they were particles, passing through one slit at a time, leaving a pattern typical of individual particles. What does this mean for us? Well, it suggests that reality doesn't decide what something is until we observe it. It's like a dance between possibilities, with a wave and particle nature of. Light and electrons exists only when we look at them. Could it be that our very observation is what makes the universe choose one reality over another? Could it be that the universe is a mirror, reflecting what we decide to see? This paradox invites us to reflect. How much of our reality is shaped by our own perceptions? In the quantum world, light and matter seem to flow through different forms depending on how we look at them. And just like these particles, we too are in a constant dance between different states, never fully defined until observed. Schrödinger's cat, alive and dead in a single moment. One of the most famous thought experiments in quantum mechanics involves a cat in a box. This is not a box of curiosity, but a box of uncertainty. Inside the box, a radioactive atom is set to decay, triggering the release of poison gas, which would kill the cat. However, if the atom does not decay, the cat remains alive. So, what happens when the box is closed? According to quantum mechanics, the cat is both alive and dead at the same time. This is known as superposition. A quantum system can exist in multiple states simultaneously, and it's only when we observe the system that it decides on a single state. The paradox of Schrödinger's cat reveals the strange nature of quantum reality. It's not just about what happens when we look into the box. It's about the idea that before we open the box, the cat is in both states. This paradox suggests that reality itself can be a blend of possibilities with no definite answer until it is measured. how does this idea relate to us in our everyday lives? Much like the cat, our futures are shaped by countless possibilities. What if, just like the cat, we are simultaneously living many different versions of our lives, only waiting for the right moment to decide which one we'll experience? Is there a moment when we too collapse all possibilities into one reality? Schrödinger's cat leaves us thinking the universe might be more fluid, more uncertain than we give it credit for. The quantum Zeno effect. Watching stops time. Imagine you're watching a clock and you notice that the hands of the clock are not moving. But there's a catch. Whenever you glance at the clock, the hands appear perfectly still, frozen in time. This phenomenon, known as the quantum Zeno effect, happens when the act of observation prevents something from changing. In quantum mechanics, particles can exist in multiple states at once. But when we observe them, they choose a particular state. If we keep looking at something constantly, it can freeze in that state. This effect is named after the ancient Greek philosopher Zeno, who argued that a runner in a race could never reach the finish line because they would have to first get halfway there, then halfway of that, and so on, endlessly. In the quantum world, particles behave similarly. When we keep watching them, they never transition to a new state. They stay stuck in the present moment, locked in their current state. The paradox here is simple yet profound. By observing something, we may be stopping its natural flow. Could it be that we, as observers, are holding the world still, preventing its progress? Does the mere act of watching make time itself seem to freeze? In your own life, how often do you find yourself watching certain moments, trying to predict what will happen, and in doing so, perhaps stopping yourself from moving forward? It's a thought-provoking idea. Time, in a sense, could be paused by our attention. The many worlds interpretation, a universe of infinite possibilities. The many worlds interpretation of quantum mechanics takes us to a place where everything is possible. According to this interpretation, every time a quantum event occurs with multiple possible outcomes, the universe splits into multiple branches. Each branch represents a different outcome, and in each branch, a new version of you exists. Imagine you are standing at a crossroads, unsure of which path to take. According to the many worlds theory, every decision you make creates a new world where one version of you takes one path and another version takes the other. As a result, there are countless versions of you, each living a different life based on the choices you've made. The paradox here is both exhilarating and unsettling. The idea that there are infinite versions of ourselves, living infinite lives, makes the universe feel vast beyond comprehension. It invites us to think about the choices we make. Is there a universe where you chose differently, where you took the other path? While this concept may sound like science fiction, it challenges us to reflect on the decisions we make in our own reality. It suggests that everything, no matter how small, creates a ripple effect, creating new worlds and new possibilities with each choice. The many worlds we cannot see exist in parallel to ours, where all versions of reality are unfolding at once. It's a reminder that life is not just about the decisions we make, but the infinite possibilities those decisions could lead to. Quantum entanglement, instant connections across distance. Imagine that you have two particles, one in New York and one in Tokyo. They are entangled, meaning that no matter how far apart they are, the state of one particle instantly affects the state of the other. This phenomenon, known as quantum entanglement, has baffled scientists for decades. Entanglement seems to defy the rules of classical physics. In classical physics, signals can only travel as fast as the speed of light. But in quantum mechanics, entangled particles seem to communicate instantaneously, even if they are light years apart. This mysterious connection between particles, called spooky action at a distance by Albert Einstein, suggests that information can travel faster than light. a concept that challenges our understanding of space and time. What does this mean for us? Could it be that everything in the universe is somehow connected, even if we can't see or understand the connections? Just as these particles influence each other across vast distances, maybe our lives are interconnected in ways we don't yet fully comprehend. Perhaps the things we do today are reaching out and influencing something across time and space, far beyond our understanding. The no-cloning theorem, the uniqueness of information in quantum mechanics, there is a profound rule called the no-cloning theorem, which states that it is impossible to create an identical copy of an arbitrary unknown quantum state. Unlike classical information, which can be copied freely, quantum information is special. It cannot be perfectly replicated. This concept may sound abstract, but it has significant implications for fields like quantum computing and cryptography. In a world where information is constantly shared and copied, quantum mechanics tells us that some information cannot be duplicated, making it inherently secure. This creates a kind of uniqueness for each quantum state. Each piece of information is irreplaceable, much like each moment in our lives. The no-cloning theorem suggests that nothing in the quantum world can ever be truly replicated. Everything is one of a kind, which makes the universe feel more personal, more unique. Think about it. Everything in the quantum world exists in its own special form, never to be copied or replaced. It's a reminder that we, too, are unique in the universe, with experiences that no one else can replicate. Quantum mechanics might seem strange and perplexing, but it offers a poetic view of the universe, one where uncertainty, connection, and possibility reign. These paradoxes, far from being simple contradictions, encourage us to question the nature of reality, time, and identity. They remind us that the universe is not fixed but fluid, open to countless possibilities, and constantly changing. As you relax and drift into sleep, consider these paradoxes. Let them lull you into a peaceful rest, knowing that even in the quantum world, everything is possible, alive and dead, distant and connected, certain and uncertain. And perhaps, as you rest, you might feel a little more at ease with the mysteries of the universe, ready to embrace the unknown. The universe we live in is full of mysteries. Our daily life, shaped by the laws of classical physics, seems like a predictable machine where everything behaves in an orderly, rational manner. A ball rolls across the ground, light travels in a straight line, and time flows relentlessly forward. Yet, when we peer into the world of quantum mechanics, this neat, predictable universe shatters. Suddenly, particles do not behave like we expect. Time is not as straightforward as it seems, and reality itself begins to blur in strange, paradoxical ways. In this deep dive into quantum mechanics, we'll explore the peculiarities that make quantum physics so mind-bending, paradoxes that challenge our very understanding of reality. We'll uncover how quantum particles behave in ways that seem almost impossible, and how these phenomena offer profound insights into the nature of the universe. Sit back, relax, and let's drift into a world where reality defies logic and invites us to think differently. Classical reality versus quantum reality. Imagine a world where things are as stable as you expect. A rock on the ground, the stars in the sky, and a glass of water on a table. All these things stay as they are, independent of whether you observe them or not. This is the world of classical physics, where the objects around us exist in definite places at definite times. If you observe an apple on a table, it will always be in the same place and in the same condition. Classical physics treats the universe as a collection of independent objects, where the observer plays no role in shaping the outcome. But quantum mechanics throws all of this out the window. At the quantum level, things are not so straightforward. Here, particles like electrons, photons, and atoms exist in multiple states at once. They are not in a single predictable position until we observe them. Before measurement, they are simply in a superposition of all possible states. Imagine that same apple, but instead of resting in one spot, it could be in several places at once, and only when you look at it does it decide to settle in one location. This is the paradoxical world of quantum mechanics, where reality behaves in the strangest of ways. The weirdness of superposition. One of the most perplexing ideas in quantum mechanics is superposition. Let's picture it. A photon, a tiny particle of light, doesn't just travel in one straight line. Instead, it can exist in multiple paths simultaneously. Imagine you are in a room with two doors. A photon enters, and instead of choosing one door, it passes through both at the same time. But once you open one of the doors to check, the photon instantly decides on one path and is no longer in both. Places. This idea isn't just abstract. It has real implications for the fundamental nature of reality. Superposition means that particles, before we observe them, are not confined to a single state, position, or velocity. They are in a combination of all possible states. Only the act of observation collapses this state into a single outcome. It's as though the universe is a sea of possibilities, only becoming real when we interact with it. Think about it. If the world we live in can only exist as one specific reality when we look at it, what does that say about the true nature of reality itself? Is it all just a cloud of possibilities until we engage with it? And if we are observers, what role do we play in choosing what exists and what doesn't? These questions swirl through the mind, challenging everything we know about existence, the observer effect, and the paradox of measurement. Now, let's dive deeper into the observer effect, the phenomenon where the act of observing a particle changes its state. In quantum mechanics, this effect is profound. Before we observe a particle, it doesn't have a definite state. It exists in multiple states at once, all entangled in a delicate dance of probabilities. But when we make an observation, the particle decides on a specific state, and its wave of possibilities collapses into one outcome. This isn't just an abstract idea. It's a core feature of quantum mechanics. The famous Copenhagen interpretation, formulated by Niels Bohr and Werner Heisenberg in the early 20th century, suggests that a quantum system exists in a superposition of states until we measure it. Only then does it collapse into a single reality. Imagine walking into a room and finding a cat, but the cat is both alive and dead at the same time. The moment you check, the cat is either alive or dead, but it is only decided when you observe it. This is Schrödinger's cat, a thought experiment that encapsulates the strangeness of quantum measurement. This paradox reveals something strange. The act of measurement doesn't just observe reality, it shapes it. The universe is not a fixed place with fixed events. It is an ever-changing possibility, influenced by who is looking. What happens when we don't observe something? Do we miss out on the full potential of reality? Do things only exist because we are looking at them? Entanglement, the cosmic connection. Quantum entanglement is perhaps the most mind-boggling phenomenon in quantum mechanics. Imagine two particles, let's call them Alice and Bob. These particles are linked in such a way that whatever happens to Alice immediately affects Bob, even if they are light years apart. If Alice's state changes, Bob's state will change instantaneously, no matter the distance between them. This doesn't just defy classical physics, it challenges our very understanding of space and time. Entanglement suggests that particles are not isolated from one another. Instead, they are deeply connected in ways we cannot fully explain. The idea that one particle influences another across vast distances challenges the idea of local reality, the belief that objects can only be influenced by their immediate surroundings. But there's a deeper implication. If all particles are entangled, Could the entire universe be interconnected in ways we don't yet understand? What if everything in existence, from the stars to the atoms in our body, is part of a grand cosmic web? Entanglement blurs the boundaries between individual objects and creates an interconnected reality that we can't perceive in our everyday experience. The role of consciousness. One of the most intriguing questions quantum mechanics raises is the role of consciousness in the creation of reality. If the observer plays such a crucial part in shaping reality, then could it be that consciousness itself is at the heart of quantum events? Some interpretations of quantum mechanics suggest that our awareness of the world is not just passive, but actively participates in shaping it. This idea raises philosophical questions that have been debated for centuries. Is reality an objective phenomenon that exists independently of us, or is it subjective, shaped by our perception and consciousness? Quantum mechanics challenges our traditional view of reality as an external entity, separate from us. Instead, it suggests that we are co-creators of the reality we experience, actively shaping the fabric of the universe with every observation. Philosophical implications. The idea that reality is shaped by the observer brings us to the realm of idealism, a philosophical view that consciousness is the foundation of all reality. This idea proposes that everything we perceive is a product of the mind, not an external, independent world. Quantum mechanics seems to hint at this by suggesting that particles exist only as possibilities until we observe them. If consciousness is required to bring them into a definite state, then could the entire universe be a manifestation of consciousness itself? These questions are not easily answered, but they invite us to reconsider our place in the universe. Are we mere observers of a pre-existing reality, or are we active participants in the creation of that reality? The answers may lie somewhere between these extremes, in the mystery that quantum mechanics continually uncovers. Conclusion. As we conclude this exploration of quantum mechanics, we return to the core mystery, the nature of reality itself. The strange and paradoxical behavior of particles challenges everything we know about the universe. From superposition to entanglement, and from the observer effect to the role of consciousness, quantum mechanics paints a picture of a universe that is far more complex than we ever imagined. We live in a world where the very act of observation shapes the reality around us, and where particles exist in a state of possibility until we measure them. This suggests that the universe is not a static, fixed place, but a dynamic, ever-changing web of possibilities waiting to be shaped by those who observe it. In this world, we are not mere spectators. We are active participants in the creation of reality. So, as you drift off to sleep tonight, think about this. Reality is not what it seems. It is not a fixed, unchanging world, but a fluid, evolving entity shaped by observation. What we experience is not the final truth. It is just one possible outcome of countless possibilities. And in the vast quantum world, the universe may be waiting for you to look at it in a new way. Have you ever wondered how the tiniest particles of the universe behave in ways that seem utterly impossible? The world of quantum mechanics, the theory that governs the behavior of the smallest things in our universe, is filled with paradoxes that can seem more like science fiction than actual science. These paradoxes, strange and mind-boggling as they may be, have the power to transform our understanding of reality itself. As we fall into the comfortable embrace of sleep, we sometimes seek out stories that are as strange as they are captivating. Tonight, I invite you to drift into a realm where the rules of reality bend and twist, where particles can exist in multiple places at once, and where information can travel faster than light. This is the world of quantum mechanics, a world where paradoxes reign supreme, and where things behave in ways that challenge everything we think we know about the universe. So let your mind wander and prepare to fall asleep to the mysterious and paradoxical world of quantum mechanics. The Double-Slit Experiment. The mystery of the observer. One of the most famous paradoxes in quantum mechanics is the double-slit experiment. Imagine a simple experiment where a beam of particles, such as electrons or photons, is fired at a barrier with two slits. The particles then pass through these slits and hit a screen behind them. Intuitively, you'd expect the particles to create two distinct patterns on the screen corresponding to the slits. However, something extraordinary happens. Instead of two distinct patterns, the particles create an interference pattern, much like waves do when they pass through two openings. This suggests that the particles are behaving like waves, not particles. But here's the real twist. When we observe the particles as they pass through the slits, the interference pattern disappears, and the particles behave like particles again. What's so strange about this is that the mere act of observation changes the outcome of the experiment. If we aren't looking, the particles behave as waves, interfering with themselves. But when we watch, they behave as particles, going through one slit or the other. This raises a profound question. Does reality only exist when we observe it? Are we, as conscious beings, somehow creating the world around us through our observations? As you lay down to sleep, think about the idea that in the quantum world, simply looking at something could change how it behaves. The idea that reality might be subjective or at least partially dependent on our observation is a concept that many still struggle to understand. Could the universe be shaped by our consciousness in ways we don't yet fully comprehend? Schrödinger's cat. Life and death in a quantum box. Next, we move to the infamous Schrödinger's cat thought experiment, which takes the paradoxes of quantum mechanics to a more tangible, albeit equally bizarre, level. Imagine this. A cat is placed inside a sealed box alongside a device that has a 50% chance of killing the cat. The device is triggered by the decay of a radioactive atom, which itself exists in a quantum superposition of decayed and undecayed states. This means that until we open the box and observe the cat, it is both dead and alive at the same time. This paradox highlights one of the most bizarre principles of quantum mechanics: superposition. Superposition is the idea that a quantum system can exist in multiple states simultaneously. So the cat doesn't have to be just dead or just alive until we open the box. Instead, it can be both, in a state of uncertainty, a quantum blend of life and death. It's only when we observe the cat that the superposition collapses, and the cat is either alive or dead. The concept of Schrödinger's cat illustrates the difficulty of applying quantum mechanics to the macroscopic world. While particles in the quantum realm can exist in multiple states, we rarely see this in our everyday experience. In our world, things seem to exist in one definite state. A cat is either alive or dead, not both. Yet, quantum mechanics tells us that reality may not be so clear-cut, especially when observed on the tiniest scales. As you prepare to drift off to sleep, ponder the idea that reality may be a state of potential until we observe it. Could your own thoughts and dreams be in a superposition, waiting for the moment of conscious observation to bring them into focus? The quantum tunneling. Passing through the impossible. One of the most mind-bending ideas in quantum mechanics is quantum tunneling. This phenomenon happens when particles manage to pass through barriers that, in classical physics, they should not be able to cross. Imagine a ball rolling towards a hill. Classically, it would need enough energy to climb over the hill. If it doesn't have enough energy, it should simply bounce back. However, in the quantum world, particles can tunnel through barriers, as if they have found a shortcut or a magical passageway that shouldn't exist. This idea was once thought to be purely theoretical, but it's been observed in nature. Quantum tunneling is responsible for a variety of processes, such as nuclear fusion in the sun, where particles are able to overcome the repulsive forces of the sun's high-energy particles and fuse together. Without tunneling, stars could not burn, and life as we know it might not exist. Quantum tunneling suggests that particles are not bound by the traditional limits of space and energy. In a sense, they can bypass obstacles that, in classical physics, would be impossible to overcome. This idea challenges our assumptions about the fundamental nature of barriers and boundaries in the universe. As you close your eyes and begin to drift off into sleep, think about how the tiniest particles in the universe can pass through barriers that seem insurmountable. Could this be a metaphor for your own life? The way in which challenges that seem impossible to overcome might, in some unseen way, be more navigable than we realize. The EPR Paradox. Spooky action at a distance. Another perplexing paradox in quantum mechanics is the EPR Paradox, named after physicists Einstein, Podolsky, and Rosen, who proposed it in 1935. The paradox involves entanglement, a phenomenon where two particles become so intertwined that the state of one particle instantly influences the state of the other, no matter how far apart they are. In other words, information appears to travel faster than light, violating the fundamental principles of relativity, which state that nothing can move faster than the speed of light. This spooky action at a distance, as Einstein famously called, it suggests that the universe might be more interconnected than we ever imagined. If two particles are entangled, a change in one particle's state will immediately affect the other, even if they are light years apart. This instant connection across vast distances challenges our traditional understanding of space, time, and causality. The idea of entanglement forces us to reconsider the fabric of reality itself. Could there be a hidden connection between everything in the universe, one that transcends the limitations of space and time? Is our perception of separateness just an illusion? Quantum entanglement suggests that the world might be far more interconnected than we ever believed. As you slip into slumber, consider the possibility that everything in the universe is interconnected, that our actions and thoughts might ripple across space and time in ways we can't yet perceive. Could everything be linked in an invisible web, and we are only now beginning to understand it? The many worlds interpretation. Infinite realities. The many worlds interpretation of quantum mechanics proposes an even more extraordinary idea, that every time a quantum event occurs, the universe splits into multiple realities, each representing a different outcome. If you've ever wondered about the roads not taken in life, the many worlds interpretation suggests that for every choice you've ever made, there's a version of reality where you made a different choice leading to a different outcome. According to this theory, there are an infinite number of parallel universes, each corresponding to a different version of reality. Every quantum decision, every observation, causes the universe to split into different branches. In a sense, there's a universe where you are living out every possible version of your life. This interpretation challenges our conventional understanding of time, space, and reality. It raises the question, how many versions of ourselves exist, playing out different scenarios in parallel worlds? The many worlds interpretation suggests that the universe may be much larger, more complex, and more mysterious than we ever imagined. As you drift off into sleep, think about the infinite possibilities of your own existence. In some parallel universe, there may be another version of you living a completely different life. The idea that countless versions of reality exist might be a strange but comforting thought as you rest, knowing that the choices we make are just one of many paths we could have taken. Conclusion. Quantum mechanics is a realm full of paradoxes and mysteries that challenge our understanding of reality. From the uncertainty of the double-slit experiment to the mind-bending implications of quantum tunneling and entanglement, the quantum world reminds us that the universe is far stranger than we could have ever imagined. As you lie in bed, ready to drift into sleep, let these paradoxes swirl around in your mind. Allow yourself to ponder the nature of reality, the mysteries of the quantum world, and how little we truly know about the fabric of existence. Perhaps, just like the particles of the quantum world, we too exist in a state of potential, full of infinite possibilities. As you fall asleep, embrace the beauty of uncertainty, and let your dreams take you to a place where the rules of reality bend and twist, and the universe unfolds in all its strange and wondrous glory. Introduction: the universe, vast and infinite, holds secrets far beyond what we can comprehend. It is a place of mysterious forces and strange occurrences, where the rules of reality bend and twist in ways that defy our understanding. We peer deeper into the cosmos. We uncover new phenomena, some of which seem to be governed by rules that exist in a realm far beyond our everyday experience. These are the paradoxes of quantum mechanics, the strange and wonderful contradictions that make up the fabric of our reality. Quantum mechanics, the science that deals with the behavior of particles on the smallest scales, has long been a source of fascination and confusion. The paradoxes it presents challenge everything we know about the universe, forcing us to confront the limitations of our perception and understanding. But rather than trying to solve them, let us embrace them, allowing the mysteries of the quantum world to lull us into a peaceful and restful sleep. In this journey, we will explore a few of these paradoxes, each one strange, each one beautiful, and each one offering a glimpse into the deeper workings of the universe. Let us relax into their mysteries, allowing the gentle pull of quantum uncertainty to guide us into slumber. The particle wave, duality. The nature of light, the first paradox we encounter, is one of the most fundamental in quantum mechanics. The particle wave duality. In the world of classical physics, light was thought to behave either as a particle or a wave. It was one or the other, depending on the situation. But quantum mechanics shattered this simple dichotomy, revealing that light, and indeed all particles, can behave as both a wave and a particle at the same time. Picture this: a beam of light passing through a narrow slit. Normally, you would expect it to act like a stream of tiny particles, each one traveling in a straight line. But when light passes through a slit, it behaves like a wave, spreading out and creating an interference pattern on the other side. It is as if the light is not a single particle, but a wave, moving through space in all directions. Yet, when we try to observe the light as it passes through the slit, it behaves like a particle once again, traveling in a straight line. This dual nature of light simultaneously, a wave and a particle, is one of the most baffling aspects of quantum mechanics. How can something be both at the same time? And why does it change its behavior depending on whether we are observing it? The answer, it seems, lies in the very nature of quantum reality. At the quantum level, particles are not fixed entities, but exist in a state of potential, a cloud of possibilities. It is only when we observe them that they choose a particular state. Until then, they exist in a superposition of states. Both wave and particle simultaneously. As we let this idea wash over us, we can let go of the need to understand it all. The quantum world, with all its paradoxes and mysteries, is not something to be solved, but something to be experienced, something to be embraced. As we drift into sleep, let the idea of this strange duality soothe you, knowing that even in the world of light, things are not always as they seem. The EPR Paradox. Spooky action at a distance. Next, we encounter another fascinating paradox, known as the EPR Paradox, named after the physicists Einstein, Podolsky, and Rosen, who first proposed it in 1935. This paradox revolves around the idea of entanglement, a phenomenon in which two particles become linked in such a way that the state of one particle instantly affects the state of the other, no matter how far apart they are. Imagine two particles that have interacted and become entangled. These particles could be millions of light years apart, but if you measure one, you instantly know the state of the other, as though the two particles are communicating faster than the speed of light. This strange connection between particles seems to defy the laws of space and time, which state that nothing can travel faster than the speed of light. Einstein famously referred to this as spooky action at a distance, unable to accept that such a thing could occur. Yet, over the years, experiments have confirmed the reality of quantum entanglement. When two particles are entangled, they are forever linked, regardless of the distance between them. This instantaneous connection suggests that space itself may not be the absolute barrier we once thought it was. As we reflect on this paradox, imagine that we too are connected in ways we cannot fully understand. Perhaps just like the entangled particles, we are all linked together, our actions and thoughts rippling through the fabric of the universe. This connection, though invisible, is real, and it binds us to everything around us. Let the comforting thought of this hidden connection lull you into sleep. Even though we may be separated by space, we are all part of the same cosmic dance, entangled in ways we cannot yet fully comprehend. A Heisenberg uncertainty principle, the limits of knowledge. Another key paradox of quantum mechanics is the Heisenberg uncertainty principle, which tells us that it is impossible to know both the exact position and the exact momentum of a particle at the same time. The more precisely we try to measure one property, the less precisely we can measure the other. This limitation is not due to the imperfections in our instruments. It is a fundamental aspect of nature itself. The quantum level, particles do not have fixed positions or momenta. Instead, they exist in a state of probability where their exact state is uncertain until we measure it. This uncertainty is inherent to the very fabric of reality, suggesting that the universe is not a fixed, deterministic system, but a dynamic web of possibilities. This principle challenges our desire for certainty, for knowing everything with absolute precision. In our everyday lives, we seek to understand the world around us, to measure and quantify it. But the quantum world reminds us that there are limits to what we can know, that there are aspects of reality that will always remain beyond our grasp. As you reflect on this paradox, allow the uncertainty to wash over you. It is not something to fear, but something to embrace. In the uncertainty, there is freedom. The unknown becomes a place of rest, a space where we can let go of the need to control everything and simply be. As you drift into sleep, let the idea of uncertainty settle in, knowing that not everything needs to be understood right now. The quantum Zeno effect. Observation freezes reality. Another fascinating paradox of quantum mechanics is the quantum Zeno effect, which suggests that the act of observation can actually prevent the quantum system from changing. This paradox takes its name from the ancient Greek philosopher Zeno, who proposed a series of paradoxes involving motion. In the quantum version, the paradox suggests that if a system is observed frequently enough, it will never undergo a change, as if the very act of observation freezes it in time. Imagine a particle that has a 50% chance of decaying over a given period. Normally, we would expect that over time, the particle would eventually decay. But if we observe the particle constantly, we prevent it from decaying, as if the act of observing it prevents it from changing. This strange effect is a direct consequence of the principles of quantum mechanics, where particles exist in a state of probability until they are observed. As you reflect on this paradox, think about the way our own lives can feel frozen in place. When we are constantly focused on one outcome, on one possibility, sometimes it is only by letting go of our constant observation, by allowing things to unfold naturally, that we can move forward. Let this thought guide you to a peaceful place where you can release your need for control and simply trust in the flow of life. The many worlds. Interpretation. A universe of infinite possibilities. Finally, we arrive at one of the most mind-bending paradoxes in quantum mechanics, the many-worlds interpretation. According to this theory, every time a quantum decision is made, whether a particle passes through one slit or another, whether a photon behaves as a wave or a particle, each possible outcome creates a separate parallel universe. In this view of reality, every decision, no matter how small, leads to the creation of a new universe, each one just as real as our own. Every possibility, every branch of the tree of existence is played out in its own universe. This means that there are an infinite number of parallel universes, each containing a different version of you, making different choices and living different lives. The thought of so many parallel worlds, each with its own version of reality, can be both overwhelming and soothing. It suggests that every possibility you've ever imagined, every path you've ever wondered about, is already playing out in some alternate universe. There is no right path, only a multitude of possibilities, each one unfolding in its own way. Let the idea of these infinite possibilities relax you. You don't have to make sense of them all. Just knowing that there are countless versions of you, living out different choices, can be a comforting thought as you drift into sleep. There is no need to worry about the future, for in one universe, everything will unfold exactly as it should. Conclusion. Quantum mechanics is a world of paradoxes, where particles exist in multiple states, where particles can communicate instantaneously across vast distances, and where the very act of observation can change the outcome of an event. These paradoxes challenge our understanding of reality, but they also offer us a deeper insight into the mysteries of the universe. As you let these paradoxes settle into your mind, remember that they are not problems to be solved, but mysteries to be embraced. The universe, in all its strange beauty, is full of infinite possibilities, and sometimes the best way to understand it is simply to relax and let go. So, as you drift off to sleep, remember that the quantum world is a place of wonder and possibility, where the rules of reality are not set in stone, but are ever-changing, ever-evolving. Let the mystery of the universe guide you into a peaceful slumber, where all things are possible and all things are connected.